Yeah, good enough.
Are there any questions? Oh, so on that notation, there, some people still have not figured it out, but,
See? I don't know.
okay. So the general notation, for those who aren't mind readers, come on, here we go. Something like that, that means given.
Oh,
So if it's usually, if it's just by itself, it means it is correct given some previous mistake.
okay.
If you see X with the squiggles, that means it is wrong given a previous mistake.
Okay.
So if I had, 5 plus blank equals 4, and then whatever that is, plus 3 equals blank, if you put 1 in there, that's obviously not correct, that would be marked wrong. I would expect 1 to be down there, and you'd write 4, so this is correct given the previous mistake,
Okay.
even though it's not really the right answer because of that.
I showed my work, okay.
Yeah, if you put 1 there, and then down here, with that being -1, the real answer was supposed to be 2. So if you had 2 down here, even though you had 1 right there, that would be wrong given your previous mistake.
Okay.
Now, in some cases, there are alternate ways of getting there, and if I can see that you did it in an alternate way, then you can still potentially get credit. On forced diagrams, correct. That means the direction's wrong. If you just have a circle, that means that there's something wrong with the label. If you have the squiggle and the circle, that means that the direction's wrong and there's something wrong with the label. If you see that I've circled something like that, that indicates you did 2 forces where I only really wanted to see one of them. So I combined them into one thing. And X is wrong. And I think that's pretty much the only marks I make. You might see BOD stands for benefit of doubt, or BOSD, benefit of some doubt. Any other marks that I've made that people are wondering what they meant? On the lab, you might also see MD, which stands for majority disagrees. Or majority does not agree or doesn't agree. I tend to put MD if you're in the minority. So you got 4 people in the group, 3 people of one number, you have a different number for data. This is stuff measured directly from the lab. You might see MD. If there's 4 people in the group and 2 of you have one number, 2 of you have a different number for the same slot, that's when I tend to do that for whatever reason. There's still no majority.
What about BUV? I think it's BUV.
Oh, on the lab, if you see some scribbling in one of the upper corners, that is the name of it's a shorthand for the name of your group.
Okay.
Because as I enter your information into my spreadsheet to know what calculations you should get, it's helpful to be able to do a quick reference to which screen I need to go to in order to the double check work. Any other squiggles? Or questions about them?
And all of this out of 10. So if you put a number up next to it, it's out of 10 for all of them?
Yes,
Okay.
yes. occasionally I might write, I was thinking on, when was grading some of the master sets, I wrote down a 1/2, that's 1/2 of 10. Just because that's the way my mind was working at that moment. So really, that's 10 halves. If it really was only half a point, then I'd probably more have to write 0.5.
I have a question about a lab.
Yes.
It was about Newton's second law in friction, and if it would still be correct. My question is, like, I believe that it would be correct because F would be total force, but in that question, do you want us to say how to, I guess, change the total force?
There are multiple approaches that you can take. So,
Is that a part approach?
yeah.
Okay.
Some people interpret that question differently, and that's fine too. Other questions? All right, we last left off with the force due to gravity, the generalized formula. The lab for tomorrow is posted. Looking at just the magnitude, oftentimes it's just easiest to look and think about what is the magnitude of the force and then think through what the direction is. Gravitational forces are attractive between two objects, and so we've done those force diagrams enough, generally with weight, but now we're talking about this. Big G, mass 1, mass 2 over r squared, or big G is the gravitational constant, although I still might refer to it as the universal gravitational constant, because some habits are hard to break. Those are the two masses involved, and r is the distance between them. So let's do a little number crunching here. So I want to figure out what is the gravitational force between me and, we'll just say that box down there, which has stuff in it. My mass is about 100 kilograms. The box down there, we'll just make the math easy. We'll see it's about 1 kilogram. The distance between us is about 2 meters. Now, if you do not have your calculator here, please at some point when you have access to your calculator, please make sure that you get the same answer as we are going to get, the correct answer that we're going to get. There are been enough students in the past that when it comes down to a quiz or something like that, they end up not knowing how to use their calculator when it deals with exponents. So it's 6.67 times 10 to the negative 11. That's G, big G, times my mass, times the mass of that box down there, over the distance between us squared. It was 1.7?
1.6675 times 10 to the negative
6675 times 10 to the negative 9th?
Yeah.
Let me write that a little bit more clearly. Units? Yep. We're finding a force. That is an incredibly tiny force there. Just to give it some perspective, the gravitational force between me and the Earth is about 1,000 newtons. Between me and the Earth. Between me and that box, when I'm 2 meters away, writing it in the same type format. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 1, 6, 6, 7, 5. So it's an incredibly tiny force between the box and me. Which is why when we're doing force diagrams, we tend to ignore it. Because it's not a particularly significant force there. I can easily walk out of the room. If the box were not here, I would walk out of the room. It would not feel any different to me. Let's take it one step further. This generalized formula right here should work. We've been using mg for weight, but we should be able to use that. So let's see if we can figure out what is the acceleration to gravity on the surface of the Earth using what we know, using that formula. So what I'm going to do is, this is the general formula here, and I'm going to set that equal to the formula we were using. All right, so I have g times mass of the Earth times mass of me is equal to mass of me times the acceleration due to gravity over here over r squared. You need a visual diagram here, not to scale. If we did a force diagram, I have this force of gravity acting on me, I have a force of gravity acting on the Earth. So the general formula, and then specific to someone who's near the surface of the Earth. So let's do some simplifying here. Do you want to get rid of anything?
Mass of me.
Yeah. Whatever my mass is doesn't matter, so this is one of the reasons why acceleration due to gravity is the same for everyone. Near the surface, near the same place. So G should just be this product here. So I have G is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times mass of the Earth, which everyone knows. So you're going to slip your mind for the moment. 5.98 times 10 to the 24th kilograms. And I know that because I've done this enough, but if you need that on a quiz or test, it'd be on the top of the first page. Over r squared, what would r be?
0.
If r is 0, why would you say 0? Because
You're standing on the Earth.
if r is 0, what would this be equal to then?
0.
Ooh. Pardon?
Could you like not do it? Impossible?
Because the math people haven't figured out how to do it yet. It is not the surface to surface distance.
Core.
Yeah, it's center to center distance. So if I'm standing on the Earth, we have the radius of the Earth and then plus to wherever my center of mass is, which is somewhere around here. And we will assume that the distance from the surface of the Earth to here is tiny compared to the actual radius of the Earth. And so what goes in here is the radius of the Earth. So this would be 6.38 times 10 to the 6th meters. Let's square that. Now I have three numbers here with the times 10 to those in it. Please make sure you know how to use your calculator to solve something like this. And if actually more than one person would be kind enough to calculate it.
0.2518 times 10 to the 7th.
Something's off. Let's make sure I didn't put a number down wrong. Oh, good with that.
Yeah, I didn't square it. Yeah, 9.8.
Which is about what we would expect. Units?
Meters per second squared.
It feels like we haven't been together for a week. The first time you got it, what was your number?
Oh, it was, I can't remember now.
Okay.
But I didn't square the denominator. I didn't
Yeah,
square all.
that's a common mistake. The other common mistake is there's a button on most of your calculators. I think it's EE.
I have E right here.
Okay, you have the EE button. That's times 10 to the, and so on the calculator, that first number, you type in 6.67, then you hit the EE button and then -11. Sometimes students will throw an extra times 10. So 6.67 times 10, EE -11, and you've actually introduced another number. You've introduced an extra 10 into the problem. So this right here stands for the times 10 to the -11. Let's right over here, just to, for those who missed it before, this is the center. Technically, center of mass to center of mass distance. Questions to hear? All right. So now what we're gonna do is we're gonna figure out if the Earth maintains its current mass, if the Earth maintained its current mass, how small would it have to become a black hole? All right. So the first thing we need to do is we're gonna launch something off of Earth. Or we'll just make it generic, some planet X. And I am launching something off of it. And I'm going to launch this thing so that it never returns. Now we are going to simplify it. This thing is not going to hit anything once it is launched. How it is launched, we do not care. We are picking up the problem as soon it's at the surface of the Earth, and it is at some speed being sent directly away from the Earth. Now, to solve this using that formula we just wrote up there would require calculus, so we're not going to do that. Instead, we're going to use conservation of energy. Because once this is launched, so we'll take another moment in time here, so it has been launched, it is right here, it is moving that way. What are all the forces acting on this object?
In space,
Pardon?
in space.
In space. There is a force acting on it.
Gravitational constant.
You see the ballpark.
Wait.
not called weight at this point. So generalize it. Gravity, huge topic, looking for a small part of it.
Acceleration due to gravity.
Wrong part. You know it. You're just afraid to say it.
Force due to gravity?
There we go. Someone brave enough to actually say the words. Yes, it's the force due to gravity. Weight is generally the term used when you're near the surface of the planet. We are now dealing with an object that is getting farther and farther away. So it's the force due to gravity. We did a force diagram, it will look like this. It is that force due to gravity. Is force due to gravity conservative or non-conservative? Chapter 7, for those who organize their notes that way.
Conservative.
Yes, it is. So therefore, since there are no other forces, I have only a conserved force acting on it, energy is conserved. So whatever energy I have here, energy at the time of launch is equal to whatever energy it has at any point along my path. Excuse me. What are the two types of energy?
Kinetic potential.
Like you mean it.
Kinetic potential.
Like you were shouting into the heavens.
Kinetic and potential.
There we go, I could hear that. You know I'm about to ask that question that you're supposed to know the answer to. So if you need to quickly flip through your notes to find it. No one's flipping notes, not many people are flipping notes, I'm assuming everyone else knows it. Here we go. What is the formula for kinetic energy?
Squared.